I've shared my screen. Can you guys see this? All right. Fine. So welcome you all to the session 7 of ADaPT. So myself Arya, and I'm a coordinator in the programming club of IIT Madras. So I'll be taking the first part of today's session, which is based on modular arithmetic in competitive programming. So let's move on without wasting any further time. So what will we learn today? So these are the things that we'll be learning today. So we'll be starting with what is modulo. I'm pretty sure that most of you have a basic idea about this particular concept. And from there we'll move on to properties of modulo arithmetic. And then a very important concept known as modular inverse. And then we'll be trying to find modular inverse using something called as Fermat's little theorem. And finally, we'll end up the session with a very efficient algorithm known as binary exponentiation algorithm. Yeah, so let's start with this. So what is basically modulo operation? It's nothing but taking remainder. It's the remainder operation. So when we say A mod n equal to B, it means that A upon division by n yields a remainder of B. In mathematics, we usually represent the above statement as A congruent to B modulo n. So that's how we read this statement, A congruent to B modulo n. Right. So in programming languages like C++, Python, we represent this operation using the modulo operator, which is nothing but a percentage symbol. So A mod B. So you can look at these examples right here. So they'll be easy to understand. 27 mod 2 is 1, 48 mod 5 is 3, 12 is divisible by 3, so hence the remainder is 0. So 12 mod 3 is 0. So focus on this statement towards the end, which says A mod n equal to B. I can rewrite this in the form of an equation, which is A equal to NQ plus B. So I hope many of you are familiar with this equation. So here the A is the dividend, Q is the divisor, and B is the, N is the divisor and B is the remainder. Q is the quotient. So in this form of the equation, we do not worry much about the quotient though. And one important condition is that this B is going to be between 0 and n. Can be 0, but the maximum value it can take is n minus 1. And one important constraint is all these must be integers. All A, N and B, all the three are integers. And n obviously cannot be 0 because division by 0 is not defined. So why do we need this? What's the purpose of knowing this to do CP? Right, so some CP questions typically based on combinatorics and probability ask you to calculate a huge number which can be outside the limits of every data type. But as it is huge, they will ask you to express it in modulo 10 power 9 plus 7. So let me show you a small code for that. Okay, fine. So I hope you can see this one. So this is a code that will give you the maximum value and the minimum value that can be stored in a particular data type. So this code as itself is not very useful for us right now. So you need not try to understand this also. So let me just run this code. So I'm using long data type because that's the common data type that we'll be using to store large numbers. So if I run this, you can see that this is the minimum number that can be stored in this long data type, and this is the maximum number that can be stored in this data type. But what happens if I cross this number? It won't throw an error, but you'll get some kind of erroneous results. So we'll look at it right now. So this part of the code I've commented it out. So I hope you know what comments are. in C++ codes. So let me rerun it. So as you can see, it gives me a warning. Integer constant is so large that it is unsigned. So we'll look at it later. So for now, I'll ignore this warning and let me proceed to run this. You can see that actually the number which I have stored is one more than the maximum number that you can see in this. This is the maximum number and I have stored one more than that. When I store one more than that, it is going back and it is outputting the minimum number that can be stored in it. So you can see that if I cross the maximum on one side, it enters the minimum on the other side. So if I try to say store 2 more than the maximum, I'll ignore the warning again. You can see it's one more than the minimum that you can see. So it's like a cycle. It's like a cycle. So in calculation, sometimes we might exceed this maximum limits, and in order to not cross the boundaries at any stage, we would generally express it as modulo 10 power 9 plus 7. But what is so special? So, I mean, most of the questions will ask you to express it in modulo 10 power 9 plus 7. So what is so special about 10 power 9 plus 7 though? It can be any number. Why is it 10 power 9 plus 7? Actually speaking, as a number, it is not special over the other possible numbers. It is just a convention to use this number as it is pretty big, out of 10 power 9, which avoids integer overflows in any practical scenarios. So it's used to, again, to stop or to avoid any kind of overflow. So this is what we call as overflow. As you can see, when we cross the maximum or cross the boundaries of a data type, that condition is called as an overflow. And it is also a prime number. So if you do not know, 10 power 9 plus 7 is a prime number, which makes it easier to calculate something called as modular inverse, which we'll be looking at it later in the session. So let's move on. Now you have a basic idea on what this topic is and why we are studying this. So could you think of an answer for this? So it's a Slido question. So you can scan the QR code and answer it. Okay, I'll stop the poll now. I can see many people have answered 3. I don't think that is the answer. So let's see what the correct answer is. So here comes our first identity, which says A mod B equal to A plus K into B mod B, where K is any integer. So what we are trying to do is that when I'm calculating A mod B, it doesn't matter if I add to it any multiple of B itself, because this part does not contribute anything towards the remainder. So the remainder for this part is like 0. So the remainder produced by this division and this division is the same. So that's what this emphasizes. Now why are we using it here? So it is because if the number is positive, it's kind of pretty direct. But if the number is negative, it's slightly confusing. So let us become comfortable by converting this into a positive number first. So I am multiplying, or I am adding a multiple of 4 to minus 151. So the closest one will be 38 into 4, which is 152. So if I compute this result, it's 152 minus 151, which is 1. So 1 mod 4 is 1. So the answer has to be 1. So I believe everyone has understood this part. Is there any doubt? So let me continue. Fine. So this is the next part. So modular arithmetic operations. It's again the basic operations of addition, subtraction, multiplication, but with the modulo m this time. So these are the identities. So a plus b mod m is basically a mod m plus b mod m whole mod m. It just says that you can individually take the modulo and then the whole modulo. So these two are same. We'll try to prove it also. And the same goes for subtraction and the same for multiplication again. You can distribute the modulo like this. And exponentiation, a power b mod m is equal to a mod m power b whole mod m. Again, once you understand multiplication, this must be similar to it because exponentiation is like repeated multiplication only. So let's quickly try proving them. So let me represent a as m into q1 plus r1. What is this? I'm just saying that a upon division by m gives a quotient of q1 and the remainder of r1. That's how I'm representing this. And b as m into q2 plus r2. So now a plus b mod m is supposed to be, I'm just substituting these two expressions into this. Now, as you can see, it is r1 plus r2 plus some multiple of m. This does not have any effect on the remainder. This contribution of this towards the remainder is 0. So I am just only taking this part, r1 plus r2 mod m. What is r1? r1 is basically a mod m. It is the remainder that is produced when we divide a with m. So r1 is a mod m and r2 is b mod m. So you can see that this is the left hand side, this is the right hand side, and the addition rule is proved. The same way you can also prove the multiplication rule. It's not very difficult. On the same grounds, it can be said that a into b mod m is, again, we'll use the same expressions for a and b. I'll just substitute these two and I'll give this. You can see that the term inside the parenthesis is r1 into r2 plus something into m plus something into m square. Again, these two terms are multiples of m only. Towards the remainder is 0. So the main term is this. So I'll write it as r1 into r2 mod m itself. So these two will be equal. Again, and then I'll write r1 as a mod m and r2 as b mod m, and this is also proved. So basically, this is for the basic rules, but we have missed something in those operations we have seen. So what about division? The division is something that we did not look into in that particular list. We had addition, subtraction, multiplication, exponentiation. Oh, what about division? So let's see what it is. Okay, division in modular arithmetic is not the same as in normal arithmetic. So it's not exactly the same. And also one important thing is that modular division is defined only under certain conditions. You can't perform this every time. So let us worry about these conditions later. First, let's get to understand what it means to say a by b mod m. Okay. So always this particular part is slightly misleading because when you see this expression a by b mod m, you would be tempted to first divide it and then take modulo with respect to m. But there is an important constraint, you know, that if I write a mod m equal to b, my a and m and b must be integers. But the result of a division may not always be an integer. If it is an integer, then it's fine, but it may not always be an integer. Say if I write some C++ code and I plug in values of a as 8, b as 3 and m as 5. So it's effectively trying to calculate 8 by 3 mod 5. So if you do the division first, 8 by 3, it's not an integer, but in C++ you know that integer division, it will truncate the fractional part and it will give me 2, 8 by 3 as 2. And if you try to evaluate 2 mod 5, you'll think that the answer is 2. But the exact answer for 8 by 3 mod 5, that the exact answer is actually 1. It's not 2. So this shows that it's not always correct to do the division first and then take the modulo. That's not very true. So given three positive integers a, b, m, compute a by b mod m. It means our task is actually to find the number c such that b into c mod m is a mod m. You can verify the result of 8 by 3 mod m equal to 1 through this expression. You just plug in those values. 3 into 1 mod 5 is 3. 8 mod 5 is also 3. So the answer 1 makes sense, right? So this is actually the exact task actually. Whenever we encounter this is what we have to do. So then we can say that A by B mod m is equal to C. So to devise a formula for modular division, that is, I have shown a kind of formula for addition, subtraction, multiplication. But what is a similar? Is there a similar formula for division? Yes, there is. But before we go there, we need to know something known as modular inverse. So, do you have any doubts so far? No, the attendance is not yet taken. The QR code will be shared towards the end of this session. If there are any doubts, you can post them. Actually, 8 by 3 mod 5 is not 2. You might think that it is 2, but the answer to it is 1. Maybe if you do the division first, 8 by 3, you will get 2, and then 2 mod 5 will give 2 only. But the answer to it is not 2. So in order to understand that, we'll have to learn more about the modular inverse. And once we get a formula for division, you can understand why it is not 2. I think I can continue. So modular multiplicative inverse or modular inverse, these two terms are used interchangeably. Okay, what is it? Given two integers x and m, the modular inverse of x mod m is another integer y such that x into y mod m is 1. So this is the statement, x into x inverse mod m is equal to 1. So this is how we represent modular inverse, x with a superscript of -1. So do not misunderstand this or do not get confused as if this is like x power -1 or if it is some reciprocal kind of thing. No. So in modular arithmetic, we deal only with integers. So this x inverse is another integer only. It's not a reciprocal of any number. So this is a very important note. Modular inverse exists if and only if x and m are coprime. So this x and m should be coprime for me to find some inverse for x mod m. So the coprime, meaning of coprime is that the GCD of x and m must be 1. The greatest common divisor of x and m must be 1. I hope that everyone knows this. And we are not interested in proving this right now. Although the proof for this is kind of a simple proof, you can check it up and you can Google it later. So, but for now, you just remember this. It exists only when x and m are coprime. Now, let us try to create a formula for modular division. All right. So let us start with this statement. Let a by b mod m equal to c. Let us say that the answer is c only. We'll try to give an expression for c, and then with that we'll get a formula for modular division. Now we know that b into c mod m is a mod m. So this is basically the task. So once I know that the answer is c, I know that this is true. Now multiplying b prime on both sides. B prime is basically the modular inverse. I'm just using this notation. You can see b prime into b into c mod m is a into b prime mod m. You might have a doubt as to how I am multiplying b prime directly into these things which are inside the modulus, but actually if you try writing out the equation, you will actually get to know that this is indeed true. You can do this. So once we have arrived here, on the left hand side of the equality, I'll use multiplication property and this relation b prime into b mod m is 1. So how am I using multiplication property? I'll take one term to be c and the other term is b prime into b. I'll use multiplication property. So this gives me b prime b mod m into c mod m whole mod m. I already know that b prime b mod m is 1. So I need not worry about that. So finally what you'll get is c mod m whole mod m. But you know the c is a result of this particular modular expression. So whenever you know that a by b mod m is c, you can directly say that c is a number that's less than m. From this you can say that c is a number less than m. Hence c mod m is also c only. You need not do anything special to that. C mod m is c only. So hence c becomes a into b prime mod m. So this is c, and we know that c is a by b mod m. Finally we can say that a by b mod m is in fact a into inverse of b mod m. So actually it's okay even if you forget this part, but this part is pretty important. A by b mod m is a into inverse of b mod m. So this is the formula for modular division. This is what we always do. All right. So do you have any doubts till now? So now we have created one formula for division. Before I proceed further, if you have any doubts, you can type it in the chat. So are you asking about that derivation part? Which part of division do you want me to repeat? Okay. So I'll start from here. I hope this part is clear because I know that the answer is C. So it means this relation is definitely satisfied because this was the task initially. So, okay, this part might be a bit confusing. So what you need to do is that it's better if you write this out in form of an equation. So I've written B into C mod m is equal to A mod m. You write it as B into C is equal to M cube plus A mod m. The similar kind of equation which you have written on the first slide, if you remember. If I say A mod m equal to B, I can write A as M cube plus B. You write a similar equation like that. And then you multiply B prime on both sides of that equation. And then you take mod m on both sides. You will end up with this. If you try it out, you will get this. After this, we are using multiplication property on the left hand side by taking one part to be B prime into B and the other part to be C. Now if I apply the multiplication property and then if I use this relation, you will get only C mod m whole mod m. Anyways, I know that C is less than m. From this equation I can say that because it's a result of a modulo m. It's definitely less than m. I can say that C mod m is C only. Finally, this left hand side is only C. The right hand side is A into B inverse mod, B prime mod m. So with that I am giving this formula. So I hope it's clear right now. Is it clear? Okay, I'll continue. Fine. So, all right. Oh, okay. So, but how to calculate this modular inverse? So we have devised a formula for division, but in this equation there is something called inverse B. So we know what it means, but how to calculate the inverse? So here we are going to use, okay, there are actually several techniques to do this, but in this we will be using something known as Fermat's little theorem. So let's move on to that. Okay, Fermat's little theorem. So this is the statement. It says a power m minus 1 congruent to 1 mod m. What it means is a power m minus 1, when I divide it by m, the remainder is 1. Under what conditions? A and m must be co-prime. So this is one condition, and m must be a prime number. Only under these two conditions is this statement valid. Now how are we going to use this to find modular inverse? Let's move on. Okay. You can write a power m minus 1 mod m is equal to 1. You can split this a power m minus 1 as a into a power m minus 2. You can split this in this form. So it becomes effectively a into a power m minus 2 mod m is equal to 1. I'll compare this to x into x inverse mod m is equal to 1. you know that this is the relation between x mod m and x inverse, a number and its inverse. This is the relation. I'll compare this to this relation. I can see that where x is equal to a, I can see that x inverse is a power m minus 2. So we can now say that the modular inverse of a mod m is a power m minus 2. But given what conditions? Obviously, modular inverse exists only when a and m are coprime. That's a condition that we have seen previously. On top of that, only when m is a prime number, I can say a power m minus 2 being the modular inverse, because only then Fermat's little theorem is valid. So we have also seen that modular division is not defined or is defined only under certain conditions. So now I can say that modular division is defined only when the inverse of the B exists. That is, B and M must be coprime. Otherwise, the modular division is not defined. That's what you can say. So if I continue from here, so finally we have given a mathematical form to this modular inverse. It's a power m minus 2. What's the next challenge? But m is 10 power 9 plus 7. How can we calculate a power m minus 2? So m is a very big number. How can I calculate a power m minus 2? This is the next challenge. So before moving on to the exact algorithm, we have to take a look at this. Actually, we do not need a power m minus 2 exactly, as it could be very large, causing overflow. So you know that the exponent is a very big number. A power such a very big number is going to be beyond the boundaries of even long data type. That's what you can guess. It's going to be very big. So what are we going to do? How are we going to tackle this problem? So we look for a power m minus 2 mod m. So this is what we call the modular inverse again. So actually you can try to understand how this is the modular inverse. Again, if you go back to this part, in this place of a power m minus 2, if I have a power m minus 2 mod m, still this equation is satisfied. You can try using the multiplication rule. Still you will get to know that even in the place of a power m minus 2, if I have a power m minus 2 mod m, still this is satisfied. So modular inverse is also a power m minus 2 mod m. Now this kind of form is good for us because it does not cause overflow. So we'll be trying to find this one. Now how are we going to find this? So the most straightforward approach would be to multiply a m minus 2 times. So this is a naive approach. I'm using long data type and I've written a function called exp, and a and b are the arguments. So what this will do is it will calculate a power b mod m, where m is you can take m to be 10 power 9 plus 7. So for the if we want to calculate modular inverse, in the place of b I can send m minus 2 as the parameter, right? So what is this actually doing? So this part is like I'm just taking a modulo m so that it comes so that everything is like within m, and then I'm creating a variable called result. I'm starting it with 1 and I'm using a for loop, and every time I'm multiplying result with a and taking a modulo of m at every stage, so that just to avoid overflow in any stage of the multiplication. In all the stages I want it to be within m, and finally I'm returning this result. So this is nothing but a very straightforward approach. I'm just multiplying a b times. I'm multiplying a b times. So the time complexity is O of b or like O of n. It's not an efficient approach if b is very large, like 10 power 10 or something. So maybe I can show it to you in code only. So I'll show this. So this is the same thing. So basically the LL is nothing but I've done hash define LL as long. So it's just a notation for long. Let me run exponentiation, this particular code. If you can see, if I just do 2 and 5, it just gives 32. This is like, for small numbers it works well. That's fine. 2 power 5 is indeed 32. If I give something very big, so say I'll give 10 power 10. Okay, there are 10 zeros. You can see that it doesn't give the output very quickly. It's kind of struggling. You can see it kind of struggles. Takes a lot of time. So I'll close it right now. So this is the shortcoming of this approach. So as the complexity is O of B, so clearly we need something better than O of B. So hence we are going to introduce a new algorithm known as binary exponentiation algorithm. Before that, are there any doubts? I'll wait for a minute. You can post any doubts if you have so far. Okay, I believe there are no doubts. So yeah, so this is the binary exponentiation algorithm. So what are we doing here? As you can see in this particular expression, a power n is 1 if n is equal to 0. So that's pretty obvious. Anything for 0 is 1. And if n is greater than 0 and n is even, we are writing a power n as a power n by 2 into a power n by 2. Fine. And if n is greater than 0 and if n is odd, we are writing a power n as a into a power n minus 1 by 2 into a power n minus 1 by 2. So this is the approach what we are going to use. So we will split the exponent by multiplying half to the exponent every time. We are going to split it. So for example, 3 power 6 is written as 3 power 3 into 3 power 3. And 3 power 9 is written as 3 into 3 power 4 into 3 power 4. And then to calculate 3 power 4, the algorithm calculates it efficiently as 3 square into 3 square. And finally 3 square as 3 into 3. So this is, with this we are able to calculate 3 power 9 with much shorter number of steps than it takes for the straightforward algorithm. Straightforward algorithm is going to multiply 3 9 times to calculate 3 power 9. But this is not doing that. So this is pretty efficient. So this is the code for that. So I'll show it directly here. Yeah. So I've just written a function called binexp, which is the binary exponentiation. Again, the parameters are a, b, which means it's going to give us a power b modulo m, and m is this 10 power 9 plus 7. This is 10 power 9 plus 7. All right. So I'll start with this. So again, I'm just taking a modulo equal to m just to make sure it's less than m. We just do this in every step. We'll take the modulo in every step. And this is the first line. If b equal to 0, return 1. This is the base case. So this is what prevents the recursion from going indefinitely. So this, at this stage it will stop and it will keep returning. Now I'm calculating a variable called res. So as you know that if n is greater than 0 and if n is even, you know that a power n is written as a power n by 2 into a power n by 2. That is what I'm actually doing. I'm calculating binexp with a, but instead of b, I'm passing b by 2. Just taking 1/2 of that exponent now, and I'm storing it in res. Now if b mod 2 equal to 0, this means that if b is even, return result mod m into result mod m whole mod m. So this is exactly similar to this particular part. This is the same thing. We're doing it in code, but we're taking a mod m because that's what we need. We need a power b mod m, and I am taking mod m at every term. But still I'm being consistent with the multiplication rule. Even if you do result into result mod m, if I use multiplication rule, this is what comes out. Because I don't want any term to go beyond m at any stage. So just for a safety, I'm doing this. And if it is odd, I am doing result mod m into result mod m into a mod m whole mod m. As you already know that if it is an odd number, I need to return a into a power n minus 1 by 2 into a power n minus 1 by 2. But you might have a doubt that result is a power b by 2. So actually this thing should be a power b minus 1 by 2. So why am I using a power b by 2 itself? So it's pretty simple. The reason is pretty simple. This is going to get executed. This statement will get executed only if b is odd. And when b is odd, right, for example, say b is 5. 5 by 2, if you do that in C++, 5 by 2 is also going to come out as 2 only. Or even if I do 5 minus 1 by 2 as it is there in this formula, even if I do 5 minus 1 by 2, it's going to be 2 only. So hence I need not call the function separately for b minus 1 by 2 also. I can use the same thing. And this will be pretty efficient. So let me run this. So this is just to show that this is indeed correct. So let me use 10 power 10 now. Okay, so you can see that the answer is like just came out in a fraction of a second. Unlike the normal exponentiation algorithm. So this is not exactly 2 power 10 power 10. So this is 2 power 10 power 10 under this modulo 10 power 9 plus 7. So this is that. Right. So do you have any doubts so far? Yeah, we can choose m in the code. Generally it will be 10 power 9 plus 7, so I just used that. So I'll wait for 30 seconds. All right. So we'll be using this. Okay, what is the time complexity before moving on? What's the time complexity of this? It's pretty clear. It's O of log b. You can see that I am dividing b by 2. In every step, I'm dividing b by 2. So the complexity comes out to be log b. It's definitely not O of b. So I'm halving b every time. So it goes as O of log b. So we will be using this function to calculate modular inverse. Let's try doing that also. So instead of taking any separate b, let me do this. What this is doing is I'm calling binx but with a and m minus 2. So this is going to output a power m minus 2 mod n, which is nothing but modular inverse of a mod n. Let us try this out. So right, let me try to find the modular inverse of 2 mod 10 power 9 plus 7. So I'll put 2. Okay, there's some problem. Oh, fine. All right. So I didn't save it. Let me do the same thing again. So if I give 2, I can see there's some very big number, 5 followed with some zeros and 4. So it says that this is the modular inverse of 2 mod 10 power 9 plus 7. Let us check it out if really this is the modular inverse. So as you know that if in case this is the modular inverse, then this into this modular 10 power 9 plus 7 must be 1. So let us see if that is true. So this into 2 modulo 10.9 plus 7 must be 1, and it is 1. So definitely this is the modular inverse. Alright, so we've seen how to use this algorithm in order to find modular inverse. So with that, I'll be closing this session. So there are the attendance form and feedback form QR codes here. Please scan it and rate the session so that we could improve in the future sessions also. I'll show it for 3 minutes. We can do it. Before that, are there any doubts also? So finally, we have successfully created a formula for modular division. And then in that formula, we saw that there was a term called inverse. We gave a mathematical form for that inverse under the condition that the m must be a prime number. Only then I can use this Fermat's little theorem. And I found out that it is a power m minus 2 mod m. And then the next challenge was to calculate how to calculate a power m minus 2 mod m. So for that, we then explored this binary exponentiation algorithm that works pretty fast, and it has a complexity of O of log b. So finally, we can perform modular division with this formula. So that will be the end of this session. So this is a summary of it. So if it is not prime, if the m is not prime, obviously we cannot use Fermat's little theorem, or we can't say a power m minus 2. So we need to use some other algorithm. There's something known as extended Euclidean algorithm. So, but we are not covering it in this session. You can, if you want, check it up later. I'll wait for 1 more minute. Fine. So I'll stop the screen sharing. So the next part of the session will be based on bit masks.
Okay. Hello. Am I audible? Hello. Okay, fine. Uh, I'm Nanda, coordinator in the programming club, and the topic of the session is bit masks and bit manipulation. I'll share my screen. Is my screen visible? Okay, I hope you're able to see the slides. These are the topics that we are going to be covering today. Some basic bitwise operations, iterating through the bits of an integer, some built-in functions, and then you will be having some one or two problems to check your understanding for what has been taught so far. Then we'll move on to representing a set in binary, implementing some set operations, iterating through sets, and then we'll look at the standard libraries bit set, and finally some more resources that you can use to learn more on your own. Okay. Okay. So we are going to be looking at some bitwise operations. So what are bitwise operations? Bitwise operations are those operations that operate on each one bit at a time. So and there are four main bitwise operations: AND, OR, XOR, and NOT. So we will take a look at the AND operation. Um, As you can see, okay, I hope all of you know that integers are internally represented as binary in a computer. Uh, do all of you know that? I'm assuming you do. So now, let us say we declare an integer variable x with the value 22. So how is this represented in binary? It's represented in binary as 10110. Now you might ask how this came to be. I'll just refresh your binary knowledge anyways. So 0 into 1, which is 0, 1 into 2, 1 into 4 plus 1 into 16. So it'll be 16 plus 4 plus 2, 22. Similarly for 26, it'll be 16 plus 8 plus 2, 24 plus 2, 26. So as you can see, 22 is represented as 10110. 26 is represented as 11010. Now, what does the AND operation do? For each bit, it produces a number that has the bits set in the positions where both X and Y have the bits set. So what does that mean? We can take a look at the example. The least significant bit, the 0, the rightmost bit, is zeroed in X, zeroed in Y, so zeroed in Z as well. The second least significant bit, the 1, over here for X it is 1, for Y also it is 1. Since both of them have 1, in Z also it is 1. However, notice the next two bits. In X it is 1, in Y it is 0. Since it is 0 and Y, in Z it is 0. So what AND does is, for every bit, it sets the output to 1 if both the inputs are 1. In all other cases, it sets the output to 0. You can see over here, we can follow the process. 0, 1 are the inputs, output is 0. 1, 1 is inputs, output is 1. And you might understand where we get the term bitwise operations, because it is doing it for every single bit, each one at a time. Now let's move on to the other bitwise operation, the OR operation. It is um, it is also a bitwise operation, and what does it do? It sets the output bit to 1 if any one of the inputs is 1. The only time it sets the output bit to 0 is when both the input bits are 0. So how does this work? The least significant bit in X is 0, the least significant bit in Y is 0, therefore the least significant bit in Z is also 0. Now moving on to the other bits, it is 1 is input, 1 is output, 1 0 is input. Since there's at least one input that is 1, the output is also 1. 0 1 is the input. Since this is at least one of the inputs is 1, the output is 1. 1 is input. Since both are 1, does not matter. It is also 1. Since at least one of the inputs is 1, here also it is 1. You can see with 22 and 26 as inputs, we get this particular binary number as output. So, are there any doubts in AND and OR? I'm assuming no. Moving on. Now we have XOR. What does a XOR operation do? Um, XOR is also known as the exclusive OR operation. It sets the output bit to 1 if the input bits are different, and it sets the output bit to 0 if the input bits are same. So what does that mean? If the input bits are 0 0 or 1 1, then the output bit is 0. If the input is 1 0 or 0 1, then the output bit is 1. As you can see in this example, with 0 0 we get 0. With 1 1 also we get 0 since both the inputs are same. With the 1 0 we get 1. With 0 1 we get 1, and with 1 1 we get 0 since 1 and 1 are same. I hope XOR is clear. Moving on to the NOT operation. As the name implies, it simply inverts all the bits. So if the particular bit is 0 in the input, then it is 1 in the output. If it is 1 in the input, then it is 0 in the output. The NOT operation is a unary operation. AND, OR, and XOR are binary since they require two inputs, whereas NOT only requires one input. As you can see over here, it just says NOT of X. We don't have any other variable. And usually int is a 32-bit, int is internally represented as a 32 bits. Therefore, I've represented the bit fully, and it sets all the 0 bits at the start also to 1. Now, I have a question for you. What will be the value of W if I print it out? You can type your answer in the chat. Uh, 1 second, my screen, what happened? Sure. 1 second, what is happening? Okay, is my screen visible? Yeah, I'm assuming it is. The answer will be negative 23, as one of you have said. How is it so? That is because in 2's complement, if we take the knot of number, we get negative of x minus 1. You can learn more about 2's complement on your own later on. This is how negative numbers are represented. Essentially, this right leftmost bit, as you can see here, will be 0 for positive numbers and will be set to 1 for negative numbers. Um, and that is how the sign is indicated. Um, why is it done this way? That is for historical reasons. Um, that's that's how it was done before earlier. But anyways, moving on. These are some other operations. These are not um, these are some other operations that you can use. The left shift operation simply moves the number how many ever times you tell it to the left. As you can see over here, this is 10110. If I tell it to move it twice to the left, it first becomes 0 1 0 1 1 0 0, and then it becomes 1 0 1 1 0 0 0. As you can see, it has moved twice to the left. Then we have the right shift operation. It simply shifts the number to the right, and whatever bits are set in um, the rightmost k bits are simply removed. So as you can see here, the number is 22 10110. If we shift it to the right by 2, then it simply um, moves the number to the right twice. So this 0 bit and this 1 bit simply get removed. Is the left shift and right shift operation clear? Okay, I'll repeat it once again. So what does the left shift do? It simply moves the binary representation of the number uh, k times to the left. As you can see over here, I'm doing x left shift twice. So it moves it twice to the left. You can, in decimal, you can think of it as multiplying by 10 power k. Over here in binary, it is the same as multiplying it by 2 power k. Okay, over here is 2 because I'm shifting it to the left by 2. So you have this 1 0 1 1 0. What happens if you shift it left to the twice? This entire block gets shifted left, and we have two zeros added to the end. Similarly, in right shift, in decimal, you can think of floor dividing by 10 power k. Over here, it is the same as floor dividing by 2 power k. Um, what is floor division? It is like integer division, the normal division that happens when you divide by an int in uh, in your C++ program is what I'm talking about. That is, it simply discards the remainder. So over here, this is the same as dividing by 2 power k. So it simply shifts the number twice to the right. As you can see, 101 is the first 3 bits. They get shifted over here. And these last 2 bits are simply removed. As an integer division, they are discarded. Does this make it clear? I'm assuming it does. Moving on. Okay. Now, one of the common tasks that you might encounter during competitive programming is to iterate through the bits of a particular number and checking if that particular bit is set. As you know, um, Usually in C++, int is internally represented as a 32-bit number. So to go through all the bits, we simply go from 0 to 32. And you have already encountered the right shift operator, and you have also encountered the AND operator. So what this does is it shifts the number k times to the right, and it checks the last bit, that is the least significant bit. If it ANDs with 1, that means that bit was set. If the AND with 1 is 0, that means that particular bit was not set. And so in the loop, we can process it however we see fit. We might want to process it if it was not set, or we might want to process if it was set, and so on and so forth. So this is how you would iterate through the bits of a particular number. Is this clear? I will explain it once again. Since int is internally represented as a 32-bit number, we would want to go through every single bit at least once. That's why we are going from 0 to 30, less than 32, so we're going from 0 to 31. What this does is, as you have seen the right shift operator, it simply moves the number k times to the right. So over here, if we move it 0 times to the right, it means it's the same number. We AND it with 1, meaning 1 is just a bunch of zeros and then 1 at the least significant bit. So if this result is equal to 1, that means that last bit was set. If it is equal to 0, meaning that last bit was not set. So if it was not set, then we can figure out if that last bit was set or not. Similarly, if I is equal to 1 going through the loop, we move it once to the right. So over here, if we move this number once to the right, we would have 0, 1, 0, 1, 1. This last 0 gets eliminated. So now when we AND it with 1, since this 1 of 1, 0, 1, 1, the last one, ANDs with 1, and we get the value of true, get the value of 1. So we can understand that the second from the left, that bit is set. And we can continue going through this loop. When I is 2, we move the number twice to the right. So we now, the last bit is this bit of 101, this bit. We can AND it with 1 and check if that bit was set, and so on and so forth. So this is how we iterate through integer and check which bits are set. Is this clear? Okay, moving on. There are some helpful built-in functions built into GCC. If you are using MSVC or Clang, then they might have different names. But Code Forces, the compiler used by Code Forces GCC, so this is mostly applicable for that. GCC exposes some built-in functions uh, to easily handle certain binary operations, bit operations. Some of the more important ones are pop count. What pop count does is it counts the number of set bits in X. There's also count trailing 0, which counts the number of unset bits at the end of X. That is the number of trailing zeros. As you can see, trailing means the end. There's also count leading 0, CLZ, which counts the number of unset bits from the beginning of X. There's a number of zeros until the first one in the beginning of X. If you are using C++20 or higher, there are functions built into the standard library that you can include from the bits header with largely similar names: std pop count, std count L0, std count R0. You can learn more about them at the resource link I'll provide. Are these built-in functions clear? So I'll explain it once more. Pop count simply counts the number of set bits in X. Count trailing 0, as the name suggests, counts the number of trailing zeros in X. That is a number of unset bits at the end of x until we encounter the first one. So over here it counts this 0 and then we encounter a 1, so it stops. There's only one trailing 0. Over here it counts the number of unset bits from the at the beginning of x. So over here there are 27 unset bits. See, over here there are 5 bits. This one is the fifth bit from the left. So over here there are 27 bits that are 0. That's what this brings up. Is this clear? Okay, I'm hoping it is. As I said before, if you're using C++ 20 or higher, there are these functions are built into the standard library with largely similar names. Pop count is pop count, count trailing 0 is count R0, and count leading 0 is count L0. You can learn more about it at the resource link I'll provide at the end. Okay, now here's a question for you guys to try. It is pretty simple. You are given two integers a and b. You have to output the smallest possible value of a XOR x plus b XOR x. Um, so yeah, simply find out the x for which a XOR x plus b XOR x gives you the minimum value. Um, Here some this question is directly taken from code forces. So ignore the first number, that's just the number of test cases. So the first test case is 6, 12. So A is 6, B is 12. And the smallest possible value that you can get for A XOR x plus B XOR x is 10, as you can see in the note. So I'll give you a couple of minutes, type your answer in the chat for what is the answer or what code you might use to find out the smallest possible value. I hope the question is clear. I'll repeat it again. You're given two integers a and b. Find the smallest possible value of a XOR x plus b XOR x for any given x. So you have to find an x such that a XOR x plus b XOR x is a minimum. Then you have to output the minimum value. So over here, the value of x equal to 4 gives a minimum value of 10. So you have to output 10. So either so mm, write the code that you would use to give the answer in the chat. Last example, what do you mean? Okay, so you are not given x, you have to find out x. I will show the question once again. I hope the numbers are clear. And if not, I will read it out. Answer for 6, 12 is 10. Answer for 4, 9 is 13. Answer for 59, 832 is 891. Answer for 28, 14 is 18. Answer for 4925, 2912 is 63, 6237. Answer for 11 is 0. Yeah, I'll give you a hint. Try and think about it for each bit in A and B. For each bit in A and B, what could be the smallest possible output value? Yes, that is correct. If we iterate, we'll get a time complex. We will have time limit exceeded. I'll give you another hint. It is we can get the answer in O of 1. That is, if we know A and B, then the answer can be calculated in constant time. I'll repeat my other hint. Think about the bits of the number, each bit of A and B individually. That is, think about what will be the minimum value for the third bit of A and the third bit of B, or the first bit of A and the first bit of B. Um, you can write out some cases and figure out what can be the minimum value that you can get for this. Okay, I believe we have spent enough time on this. The answer will simply be A XOR B. How is this so? Let us think about it one bit at a time. Let us say the first bit of A and the first bit of B. What are the possible cases that we can get? They can either be 1 1, 1 0, 0 1, or 0 0. Let us tackle the case when the first bit of A is 1 and the first bit of B is 1. Now, if both of them are 1, then x, the first bit of x, could have been 1, which would then make 1 XOR 1, which would be 0, 1 XOR 1, which will be 0. So we'll get the value as 0. Let us tackle the case of 1 0. Now, no matter what we choose as x, in the output, at least one of them will be 1. Since if we choose x as 0, then 1 XOR 0 would be uh, 1 XOR 0 would be 1. If we choose x as 1, then 0 XOR 1 would be 1. Similarly, for 0 1 also, no matter our choice of x, the answer would be 1. For 0 0, we can choose x to be 0, in which case 0 XOR 0 is 0, 0 XOR 0 is 0, and we add them, we simply get 0. As you can see, if we write out this case table, we get that for each bit, the minimum value is simply the XOR of those. So since XOR is a bitwise operation, we can simply apply this for each and every bit, which is what A XOR B does, and we get the minimum value that is being asked for. Is the example clear? I'm hoping that it is. Moving forward, here's another question. Initially, you have a box. Initially, it is empty. Each morning, you put some number of bacteria in the box, and each night, every bacteria in the box will split into two. You want to see exactly X bacteria in the box at some particular moment. So, what is the minimum number of bacteria you need to put in the box across those days? So, to give an explanation, Let us say I hope to see exactly 5 bacteria, which is in the first example. Then I add one bacteria in the box in the first day's morning, and by the third morning there'll be one into two, 4 bacteria. Now if I put one more, there'll be 5. So we added 2 bacteria, so the answer is 2. In the second example, I want to see 8 bacteria. So I simply put 1 in the first morning, and by the fourth morning, it will be 1 into 2 into 2 into 2, so 8. So output the answer, that is the minimum number of bacteria you will need to add into the box across the days. Is the question clear? I will show the question once again. So you have a box which is initially empty. Every morning you can put any number of bacteria in the box, and at night every bacteria in the box will split into two. You hope to see exactly k bacteria at some point in the box at some moment. What is the minimum number of bacteria you need to put in the box across the days? Now, of course, if I give you x, you can put x bacteria on the first day, but that does not minimize the number of bacteria we need to put in the box. So think about it. I have shown you a function that exactly calculates this as well in the previous slides. Yes, that is correct. We simply have to find the number of set bits. And how do we do that? We can simply use the built-in function pop count, which will be the number of set bits in X. Why is this the answer? Because if we look at the binary representation of X, each set bit in that would have been one bacteria at some point in the past that has been multiplied by 2 to come to this point. So we simply just have to add the number of set bits in X. We simply just have to find the number of set bits in X, which we can do using the pop count function. I hope this example is clear. Yes, using pop count. Okay, moving on. We can efficiently represent a set of up to 31 elements, 31 distinct elements using an integer. How do we do that? We can simply set the particular bit to 1, indicating if it's present in the set, or to 0 to indicate if it is not present in the set. Um, there's some common operations that we might want to do in this. I think you might have seen the STL set in the previous sessions. So how do you insert into the set, insert into an STL set? You simply do dot insert. Over here, we simply have to make the kth bit to be 1. And we don't care if the kth bit was 1 earlier. We simply want to, simply want it to be 1 regardless of whether it was 1 or 0 in the past. So what does the OR operation do? If initially it was not set, now it becomes set. If it initially was set, then there's no change, which is exactly what we want. It inserts the um, it sets the pth bit to 1 and does nothing if the pth bit was already 1. Now how do we delete? This is an interesting operation. In STL set, you might have done dot erase and passed in the key. Over here, we want to unset the pth bit. So how do we do that? You might have remembered the not operation, which sets all other, which inverts every bit in the number, and this is exactly what we want. Um, we want to make pth bit to be 0 and all other bits to be 1 and with x. Why do we want all other bits to be 1? So that it doesn't interact with the and of 1 and something is simply that something. So setting all other bits to 1 does not interact with the other bits apart from the pth bit, which we set to 0, so that if the pth bit was already 0, then it does nothing. However, if the pth bit was set to 1, then it sets it to 0, thereby removing it from x. Moving forward, how do we toggle a bit? Or how do we, what I mean by toggling is, let us say the pth bit was set, then if I toggle it, I want it to be unset, and if it was initially unset, I want it to be set. Um, what is the binary operation that does exactly this? That is XOR. What does XOR do? If initially the bit was 0 and I XOR it with 1, then it becomes 1. However, if initially the bit was 1 and I XOR it with 1, I get 0, which is the behavior that we want. So if P is an X, it removes it, otherwise inserts it. Then finally the cardinality of the set, which is the number of elements, which is simply be equal to the number of set bits. Okay. I hope you understand why we do one left shift P. Since we are indicating the presence of an element using the bits of the integer, each bit represents whether that each the kth bit represents whether k is present in x or not. So if we want to generate just a set containing the kth bit, we simply do one left shift that many bits. That will make a bunch of zeros, the kth bit 1, then another bunch of zeros. I hope this is clear. Moving forward. So this is how you would implement basic set operations. I mean insertion, deletion, toggling, and cardinality. Now for some set operations that you might have learned in high school, there's union, which I hope you know what union does. Union simply makes a new set which contains all the elements of the other two sets. In this case, I'm taking two sets x and y, and z, I want z to be the union of x and y. How do we do that? We do or. And why does or work? If a particular element is present in either x or in y or in both, that bit will be set in z, which is exactly what we want out of union. Moving on to intersection. What does intersection do? It should only have the particular element set if both of them have it, which is exactly what the bitwise AND operation does. It outputs 1 only if both inputs are 1. Then we have the complement. In this case, I'm taking the universal set to be a set with all ones, all 32 ones. So to find the complement, we can simply do not of x, which is the same as universal set minus x. Uh, and then finally set difference. What is set difference? It removes all elements in x that are present in y. How do we do this? We do x and not of y. Why does this work? Let us say a particular element is present in x and it is present in y. That means the kth bit is set in x and the kth bit is set in y. When we do not of y, the kth bit becomes unset. So when we do x and not of y, the kth bit in x, which is 1, ANDs with the kth bit in y, which is 0, the kth bit in not y, which is 0, so the answer is 0. However, if y does not contain that element, that means the kth bit in y would have been 0, kth bit in not of y would be 1, 1 and 1, that is the kth bit in x and the kth bit of not y would now be 1. I hope you understand how union, intersection, complement, and difference are implemented. Okay, moving on. How do we iterate through every possible subset? Um, Moving forward, there are a number of algorithms that might require you to traverse through all subsets of a particular set. How do we do this? If your set contains m elements, this is how you do it. Sorry, if your set contains n elements, this is how you iterate through every possible subset. Um, X equal to 0 represents the null set. We start from there and we go through the every single subset. And as you can see, m is 1 left shift n, which is the same. So m is equal to 2 power n, which is equal to the cardinality of the power set containing n elements. Now, suppose we do not have a set containing n elements, but a particular set, and we want to iterate through the subsets of that. This is how you would do it. This goes through the subsets in the increasing order, first in cardinality and then lexicographically. First in cardinality, then lexicographically. Initially starts at the null set and proceeds further. And inside these for and do while loops, we can process that particular subset. Is this clear? I'll repeat it once again. If you want to iterate through the subsets of a set containing n elements, you can do it like so. If you want to iterate through a particular set, then you do it in this way. And they go through the subsets in the order first in cardinality. If the cardinality of the subsets are the same, then it goes through lexicographically. Finally, we have seen how to represent sets using integers, but with integers we run into the limitation that uh, we can only encode 32 bits. Using a long or a 64-bit integer, we can go up to 64 bits. However, if we want a higher number of elements in our set, we can turn towards the bit set, which is included in the standard library, and you use it like so. You include the bit set header, or if you are including using bits did c++.h, then it'll already be there. You declare it passing in the number of bits you want as a template parameter. Um, and you can use this if you know beforehand the number of elements that your set is going to contain. If you do not know that and you want to read it in as user input, there is an extension library provided by GCC under the TR2 directory, which contains the dynamic bit set. And using the dynamic bit set, you can construct a bit set of n elements at runtime. That is, if you do not know the number of elements in your set beforehand, you can use the dynamic bit set. However, if you do know it, you can use the normal bit set provided by the standard library. Note that this header is only available in GCC. I do not know if it will work with Clang or MSVC. Close show the code once more. Yeah, okay. The slides will be shared anyways, so you don't need to worry about that. But here it is. Okay, I hope you got the code. Uh, that's about it for the presentation. Here are some resources that you can use. A large amount of material for the slides were drawn from the Competitive Programmer's Handbook. And re relevant information to the slides start from page 105. Here's the URL. There's also CP algorithms, which contains some more algorithms involving bit manipulation, and you can take a look at bit set and the bits library in CPP reference. So thank you. And here are the attendance and feedback QR codes. Please do uh, give us feedback so that we can improve our sessions in the future. Thank you. If you do have any doubts, write it in the chat and I will take a look at it. Okay, there are no doubts. I will end the session.